Strong acid versus weak acid. We know that a strong acid, like I have here on the left-hand side, 100% of the acid molecules are going to dissociate into an H plus and an A minus. Versus a weak acid, less than 100% is going to dissociate into the H plus and the A minus. We call this partial ionization, and that is what makes a weak acid weak. Not every single one of the acid molecules breaks into ions. Strong means every single one, 100% does. So if I wrote the chemical equations for these generic acids, your strong acid, HA, is going to break up into H positive and A minus. And if I was to write equilibrium constant expression, a K value, we would do the same format as Kc, Kp, Ksp, all Ks follow the same format, products divided by reactants. And so Ka is the concentration of H positive times A over the concentration of HA, all at equilibrium values. But since HA is a strong acid, the concentration of hydrogen ion and the anion are going to be very, very large. This is a very product-favored process. And so if the products are very large at equilibrium, we have a lot of them, the value of Ka for a strong acid is extremely high. This essentially is going to go to completion, and you essentially have zero HA down here. And so your Ka values for strong acids, they're so large, we usually don't even report Ka values for strong acids. Kas are too large for a strong acid. Now let's compare that to a weak acid. So here we have Hb, and I've drawn this differently. I've used a double arrow for this weak acid because this is going to be a reversible process. Your hydrogen ion and this B negative can reform that Hb. I can also write a Ka expression for this weak acid Hb. It's going to be H positive B minus over the concentration of Hb. Again, all equilibrium values. But because this is a weak acid, notice that you have very little amount of the products. This is very, very low value. But your Hb, that weak acid, is very large. So since Ka is products divided by reactants, values for weak acids, their Ka values, you have a very low value in the numerator divided by a very large value in the denominator. So you're going to get very small numbers for Ka. The weaker the acid, the smaller the Ka value, and because you're going to have very few products at equilibrium and much more reactants because not a lot of the acid is dissociating and producing the ion products. So this table summarizes the difference between strong and weak. We know strong means 100% dissociation, weak is less than that 100%. Ka values for strong, they're really large. Equilibrium lies far to the right. That means lots and lots of product. The concentration of hydrogen ions at equilibrium is going to be essentially the starting concentration of the acid. And A minus, the conjugate base of that strong acid, is much weaker than water. Versus a weak acid, Ka is going to be really small. For a weak acid, it lies far to the left in its equilibrium position. Left-hand side of that arrow means we're going to have lots of reactants. And the concentration of hydrogen is much less than the initial concentration of the weak acid. That's super important when we get to pH calculations of weak acids. Because unlike strong, where we can just plug in the initial strong acid concentration as the hydrogen ion concentration, we cannot use the initial hydrogen or the initial acid concentration here as hydrogen concentration because this is a weak acid. The conjugate base, A minus, is going to be much stronger than the water when you're dealing with a weak acid. So here are some common Ka values for some weak acids, and it's listed here in decreasing Ka values. So 10 to the negative 2 here at the top, 10 to the negative 10 down here at the bottom. The larger the Ka value, the stronger the acid. So these guys up here are stronger acids than these ones down here. And for each one of these, I could write a dissociation equation. So for hydrogen sulfate ion, we could take HSO4 minus. We can put that in water. By definition, an acid gives away its hydrogen. So this acid is going to give away its hydrogen and turns into the sulfate ion. And water here is acting as a base, and when it accepts that hydrogen ion, water turns into H3O plus, known as your hydronium ion. This means the same thing as H plus. Right? Hydronium and H plus mean the same thing. A lot of times we just simplify it and just write H plus instead of hydronium. This is going to have a Ka value of 1.2 times 10 to the negative 2. Okay, I'm going to repeat a dissociation equation for the acid here at the very bottom of this list. You have HOC6H5 in water. It's going to lose that hydrogen that's attached to the oxygen. And you're going to end up with OC6H5 negative plus hydronium. And here's the difference, because this first acid has a Ka value of 1.2 times 10 to the negative 2. The second one has a Ka value of 1.6 times 10 to the negative 10. Based alone on those Ka values, this first one here is the stronger acid between these two. And so what does that mean in terms of equilibrium and the position? This first acid is more product favored than this one. So if the size of these green arrows show you how product favored these acids are, the first one is going to produce more product than the second one. And that's why its Ka value is going to be larger. So the Ka value shows you the extent to which that acid produces ions and dissociates. The bigger the Ka value, the stronger the acid. Looking at some examples for calculating pH, let's calculate the pH of a 3 molar solution of hydrocyanic acid, HCN, and I'm given its Ka value. For weak acids and bases, we cannot just plug and chug into the pH formula because the concentration of H plus at equilibrium is much less than the starting concentration of the weak acid. I have to create an ice chart. We're going to start by writing the dissociation equation for this weak acid. And this is why also knowing the strong acids are so important, because HCN is not one of my 6 strong acids, so I have to know that this is weak. Therefore, I must do ice. So I have an aqueous solution of hydrocyanic acid. It's going to produce hydronium ion and its conjugate base of Cn minus. I can write the Ka expression for this reaction. Ka is equal to hydronium cyanide over concentration of hydrocyanic acid. Oops, and I made a mistake. Water is not aqueous. Water is a liquid, and we know liquids do not go into our Ka or equilibrium constant expressions, just like solids and liquids from before from Kc and Kp calculations. Okay, so our initial concentration of The weak acid is 3 molar. So that's our I in our ICE chart. I can ignore the water since it's a liquid, and 0 of our product ions to begin with. The change are going to be the X's, minus 1X from hydrocyanic acid, plus 1X, plus 1X for our products. And then so at equilibrium, hydrocyanic acid is 3 molar minus X, hydronium is X, and the cyanide is X. We need to solve for the hydronium ion concentration because that is H plus. And I know if I can get the H plus concentration, I know pH equals negative log of H plus. I need to plug in the equilibrium value of the hydrogen ion, aka hydronium. So I essentially need to solve for X and plug X into the pH formula. So I have a Ka expression written here. I'm going to plug in X for hydronium, X for cyanide, and then that 3 molar minus X for our hydrocyanic acid. So Ka was given to me 6.2 times 10 to the negative 10 is equal to X for the hydronium and X for the cyanide, and then over 3 molar minus X. So these are equilibrium values according to my ICE chart. Hydronium is X and the cyanide is X as well. Now I need to solve for X. And you'll notice here, if I left it this way, it's going to be a little bit of tricky math. With Ka ICE charts, we're allowed, like in those KSP ICE charts, we're allowed to ignore this minus X part because X is going to be so small, it's going to not affect the molarity of the weak acid. Okay, essentially the molarity of the weak acid at equilibrium will be the same as the initial concentration of that weak acid. So I'm going to make myself a little note here. Since X will be much smaller than the starting concentration of HCN 0 initial, which was a 3 molar, we are going to ignore that minus X. So this simplifies things a bit for us. 6.2 times 10 to the negative 10 is now equal to X squared over 3. Solving for X, X equals 4.3 times 10 to the negative 5 molar. X, according to my ICE chart, is H3O plus, the hydronium ion concentration. So therefore, pH is negative log of H, and I know H and H3O plus are one and the same. So pH equals negative log of 4.3 times 10 to the negative 5. I get an answer of 4.365. And now looking at sig figs, your Ka value only has 2 sig figs in it. So we're going to keep 2 decimal places for our pH. 4.37 is the final answer. Example number 2. Let's calculate the pH of a 15 molar ammonia solution given its Kb value 1.3 or 1.8 times 10 to the negative 5. So now they give me a Kb value. Well, I know Ka is the acid equilibrium constant. Kb is going to represent a base equilibrium constant, B for base. And I know ammonia is going to be a weak base because it has that nitrogen on it, and that nitrogen is really good at attracting positive ions such as a hydrogen ion. So first we're going to start by writing the dissociation equation for this weak base. Ammonia in water. Bases by definitions take hydrogens. So it's going to really steal one of these hydrogens off the water. And you can think of water as HOH. It's going to take off one of those hydrogens and it joins the ammonia. So you end up producing NH4 positive aqueous ion, and what's left over from the water after you've taken away the hydrogen is a hydroxide ion. Producing that hydroxide makes this a very basic solution. By definition, you're going to produce a base here. I'm going to start by writing our equilibrium constant expression like we did for our Ka example. Kb is equal to the concentration of ammonium ion times hydroxide over NH3. Again, ignoring the water because it's a pure liquid. Let's complete an ice chart for ammonia. It's starting with a concentration of 15 molar, 0 for our products, minus X, plus X, plus X. So at equilibrium, ammonia is 15 molar minus X, ammonium is X, hydroxide also X. And we're going to solve this the same way as the Ka problem, and we want to solve for X because I noticed that X in a Kb ice chart, X is hydroxide. And if I know the concentration of hydroxide, then I can calculate pOH and then calculate pH from there. So we're going to plug and chug. Put in your Kb value given to you, 1.8 times 10 to the negative 5 is equal to X squared over 15 molar minus X. And just like before where we said X is going to be so small in comparison to the initial concentration of the weak acid, we can say the same thing. X here is going to be so small in comparison to the initial concentration of this weak base, it pretty much can be ignored. So you're going to ignore that minus X because X is much, much, much smaller than the initial concentration of ammonia. So it becomes 1.8 times 10 to the negative 5 is equal to X squared over 15. And solve for X. X is equal to 1.643 times 10 to the negative 2 molar. And since this is a Kb ice chart, X is equal to hydroxide. Once I have hydroxide, I can calculate pOH. pOH is the negative log of OH. I plug in 1.643 times 10 to the negative 2. I get a pOH value of 1.7843. So therefore the pH is 14 minus 1.7843, and I get 12.1212 as my pH answer. So you might be asking yourself, well, when can I ignore that X and when can I not ignore the minus X in these ice charts? For our purposes in our class, it's pretty safe to assume that you can ignore that X, but just make sure you note on your paper the reason why you're ignoring X. But if you want a hard, fast rule, take your Ka value or your Kb value and multiply it by 100. So this Kb value was 1.8 times 10 to the negative 5. So I want to take that 1.8 times 10 to the negative 5 times 100. Okay. 1.8 times 10 to the negative 3. Compare that to the initial concentration of our weak base. It was 15 molar. When your Kb times 100 is less than the initial concentration, we are good to go. You can ignore X. This is known as that 5% rule. Because if the dissociation is less than 5%, you can pretty much ignore X. Okay, so multiply your Ka or your Kb value by 100. If your answer to that is less than the initial concentration of the weak acid or the weak base, you're good to go, ignore X. But if it was greater than, then you cannot ignore that X. But in this class and on that AP exam, it's pretty safe to assume that you can ignore X because of this 5% rule. So calculating this percent dissociation, calculate the percent dissociation of the acid in example number 1. We're going to keep it very simple. How do we know that it is less than 100%? How can we actually calculate the percentage of the acid that is dissociating? Percent dissociation of an acid is equal to the X from the ice chart over the initial concentration of that weak acid. Then multiply by 100. If I had given you a problem with a base, it's still X over concentration, but now instead of acid, you put in the word base, still over the initial, times 100. So I'm asking you to solve for the percent dissociation of the acid in example number 1. So our percent dissociation of the hydrocyanic acid, take our X value from our ice chart. It was 4.3 times 10 to the negative 5. Over the starting concentration of the acid, it was 3 molar. And you multiply by 100. We get a percentage of 0.0014%. Or you can put it in scientific notation, 1.4 times 10 to the negative 3% dissociated. So this is definitely following that 5% rule. Hydrocyanic acid only dissociated by 0.0014%, well less than that 5% and really less than that 100%, and that's what makes it a weak acid.